Okay, Windows native API. Now, in the normal way of doing things, it's good to say what you're talking about, but also what you're not talking about. I'm looking at the layer just below the Win32 API. If that means nothing to you, you may be in the wrong room. I'm not talking about writing a Windows kernel device driver, or how all the wonderful systems that hide inside the Windows OS work. I'm looking just at the little layer that sits between application space and what happens in the kernel. So that's what I'm covering. A bit of background about me. I'm a computer programmer, like many of you, I imagine. And I work on both Windows and Linux. I've used Windows for a while. But I'm the sort of person, I like knowing what's happening underneath my feet. What is under this stage? So how many of you are like that? You're using something at a fairly high level, but you like some idea of what's going on the layers beneath you. We've heard a bit this week about full stack development. I feel that actually having an idea of what layers am I built on top of. Now, many moons ago, when some of us were much younger than we are now, you could almost believe you understood the computer. Now, of course, it's really hairy, and if you actually tried drawing out the full list of all the layers that there are between you and a few electrons somewhere down the bottom, we could probably be here all morning just filling in all the layers. You know, you think you're operating instructions on a computer. No, you're sending instructions to a whole micro program that's running inside your chip that's doing all sorts of clever things, but we won't go there. So that's what I'm hoping to look at, is just this little thin layer to give a bit more understanding about how applications running in user space on Windows NT. Who remembers what NT stood for? New technology, yeah, it's a great name, isn't it? Windows OT, which has been around for a while now, and what the interaction is. So, in common with many, almost all, apart from perhaps some rather esoteric kind of real-time operating systems, Windows got two modes. The chip may have more modes than that, but Windows uses basically two. You've got, I'm an application, I've got a very constrained environment, I can do certain things legally. Many of the instructions that the beautiful guys at AMD and Intel have provided are not available to my program. If I try using them, what happens? Anyone seen this? Illegal instruction? Yeah, some sort of access violation or error. Your program just, you can't do that. Sorry, you've got a much smaller vocabulary in application space. Of course, how many of you actually write programs in assembler? Ooh, more than I expected. Jolly good. Most of us use a language that doesn't really let us do much assembler, unless we do a bit of inline assembler. Apart from those nice guys at Microsoft who decided that inline assembler in an x64 compiler wasn't needed and took it out. So you have to do all this stuff with 0x whatever, comma, 0x whatever, and declare bytes to get instructions in it. Oh, well. And then below that, you've got, actually, Kevlin. Who was here for Kevlin's talk just now, where he was talking about trees and how programmers' trees have the roots in the air and everything. So I think I can say beneath us, we have the higher privilege. Operating, well, whatever. We have the operating system. Maybe side by side will work well. And in the operating system, it has control of everything, all the memory, all the peripherals. It knows about all the processes that are running. It can do stuff that we can't. Of course, anyone that knows much about Intel will know that the Intel chip's got 4 priority levels. 0, 1, 2, and 3. And we tend to live at the opposite ends. I've been told if I was in Italy, I shouldn't do that. 0 and 3. Anyone know what happens to 1 and 2? Anyone remember OS2? Yeah. Anyone know about IOPL2 on that one? They had this clever mode where you were running partly trusted. So level 2 gave you direct access to I/O ports, but you couldn't do things like reprogramming the memory layout on the machine. But it turned out, historically I gather, what happened was when Windows NT was being designed, they thought about doing something with level 2, and then they were actually looking at implementing Windows on top of more than one architecture. Who's ever used the Alpha chip? That was fun, wasn't it? Memory model, it was interesting. But not all the chips they were looking at targeting supported more than 2 levels. So they just decided, for simplicity, we're trying to write a portable operating system. We'll go with just the 2 levels. I decided fairly early on in the Windows NT days that I would probably stay away from the Ring 0 stuff, the operating system stuff. And there's 2 reasons for that. One is I'm a bear of very little brain, and you can't get everything in your head. And the second, and perhaps more important reason, was I've been working a lot in places like banks. And they look a bit sniffy at anything that gives you access to the kernel for reasons. So you're stuck in user space, which is fine. You can do a lot in user space. So the application trolls along doing calculations, as you do, with numbers and strings and things. And then at some point, you need to make a system call to do something, like print some output, or read from a file, or the list goes on. So something's got to change the mode so you get your thread of execution gets into the kernel. You want to do some sort of sanity checking that the request makes sense. Which request was it? Do the parameters make sense? Are you requesting something you're allowed to do? Because different programs have got different rights. And then it does the stuff, returns you the data, or maybe it just does stuff and you get a notification back that it worked or didn't. But it's quite rare, very rare, to actually make a direct call to one of these native APIs. They all start capital N, little t, presumably for Windows NT, I guess. Who's ever written some code that does a direct call to one of the NT calls? Yeah, good. You may not learn much this morning, but you never know. Most of us don't. Many of us write code that uses a language, a high-level language, or even a language like C or C++. And we call things like, we use IO streams, or maybe we are slightly lower level and we call printf. Who's ever used printf? Yeah, we're among friends. That's good. So, we're in here, and we call stuff in probably our language runtime. And some of the things we call in the language runtime stay in the language runtime. The one on the right. And others of them go down and call into the operating system API, the Windows 32 subsystem. And some of those stay in the Windows 32 subsystem, but not all of them. Some of them go further down through the Windows native API into the kernel and come back up. But of course, many environments have various degree of backdoor where you can call into either Win32 API or the NT kernel direct. And even things like .NET let you import Win32 DLLs or NT DLL and write the appropriate wording to get the arguments right, and you can make more or less direct calls. A bit of magic happens to convert the parameters and you end up in here or in there. So, consider this program, which, as you can see, the formatting has translated correctly. Imagine the box moved slightly. Hash includes cstdlib, int main, exit 42, which of course is the only exit code you're allowed. What's it do? There's a simple answer and a complicated answer. What's the simple answer? It exits, yep. With what value? 42. How do you know? You check the return code from your call to create program. What really happens, if you actually follow through with a low-level debugger and look at all the stuff that this little program does when you run it, it's quite terrifying. But we'll stick with exit 42, which goes under the covers and eventually invokes the Win32 function called exit process. Different naming convention, but does basically the same thing. And this in turn does stuff, partly documented, partly not, and ends up calling the Windows native function nt terminate process. Okay, So we've got this kind of onion-like approach where we go through. And one of the things you'll discover with the Windows native API is the degree to which there's any kind of correlation between the functions you call in your application and the functions you call in the native API varies widely. So some of them, there's a really clear one-to-one correlation, and others, it's a lot muddier than that. And again, back off by one. Who remembers when Windows NT was new or newish? And it supported the Windows 32 subsystem. It also supported other subsystems. POSIX, OS2, yep. So the NT API was designed so you could plug different personalities on top, or at least Microsoft could plug different personalities on top. And so some of the calls were designed to be kind of generally useful for different sorts of operating system-ish interface, which are all loosely from the kind of what you might call Unix and its wider family of operating systems. So there's a lot of commonality, but some differences. As time's gone on, each version of Windows and each mini release of Windows tends to add a few more APIs to the native API. And some of them, what happens is you look in NTDLL and there's a new couple of native APIs and you think, oh, that's interesting, I wonder what they do. Well, I'll take the NT off the front and Google for that. And it turns out there's a Win32 API with exactly the same name and exactly the same number of arguments. And you're a bit suspicious that the implementation will just be a jump. And sometimes that's all it is. And others that there's really no, as I said, no relation at all. Well, let's change it slightly. How about we just do return 42? We've not used the C runtime now, have we? Well, not implicitly. But of course, how did we get there in the first place? Int main. That's not where the operating system loader starts execution. There's a whole bunch of stuff that's happened in the C or C++ runtime first. There's a whole bunch of stuff that happens afterwards, and it's loosely as if we'd called exit. Loosely. What's different between this program and the other program? I'm not explicitly calling exit, so it may not call exit. It will do the same things. Some of the issues about, supposing I had some local variables in my main, and I call exit, what happens to destructors? Yeah, there's a few differences between return and exit. It may matter, it may not. But we can go one level lower than that. We can call exit process ourselves. How about that? With 42. You will undoubtedly not be surprised to realize this program too has a return code of, you guessed it, 42. So it's all good so far. However, the language runtime doesn't know anything about exit process. So there'll be a certain amount of tidy up that you probably take for granted in C++ or C that kind of clears things up, winds things down, that you may just kick sideways if you call exit process, because you're going one level behind. You're jumping a complete level of abstraction. But this may be a good thing. Many years ago, I worked on a project where we used quite a lot of third-party libraries. And one of them, in its destructor, tried invoking a virtual destructor in an object that had been created in another library that had been unloaded. So it jumped to code in the DLL that had gone. And we tried working around this, and we couldn't, and it was all third-party code. So we changed it to just call exit process. We don't want to try and call the destructors because they're doing bad things. We can go further. We can terminate with extreme prejudice. We can get our current process ID and we can call terminate process me with the same number. And then we can go further still, and we can call the underlying NT terminate process. But it's not quite as easy as that, because they don't give us a header file with NT terminate process in. Or at least I couldn't find one, which is not necessarily quite the same thing. So you have to write this. And I've color-coded it to say, oh, there's things here I should remember to mention. Extern C, it's C callable, which I guess makes sense if you think about it, because that's often the ABI layer that you have for operating systems, because everything speaks that. Extern C, it returns NT status. Whatever. That is in a header file. It's a 32-bit int. I want 64 bits. It's a 32-bit int. All right, whatever. NT API, that's the calling convention. Now, who remembers the joys of all the multiple calling conventions there were on 32-bit Windows? Who misses those days? Yeah. Who is appreciating the fact that Windows now has two 64-bit calling conventions? Yeah. It shouldn't really matter. You could probably take that out on 64-bit and it would still work, but I haven't tried it. And then you put in NT terminate process, and the convention when they're documenting these, because some of them are documented, do you know why? We'll come to that. We have in, it takes a handle of the process, and it takes, oh look, the same thing again, an NT status value. So our Win32 program, when it actually terminates, it's going to pass a 32-bit NT status value into the kernel, and that will be the status value we return. Of course, in C, we think int. And in fact, it's a 32-bit unsigned value. Does this matter? It's just interesting that the layers are slightly different. Once we've got that, we can now call it. We get the current process, and we pass it in as the first argument. Aha, you think, but is this going to work? I've called a Win32 API to get my process ID and get my handle back, and I'm passing that to a native API. Does the word handle mean the same in both contexts? Sometimes, but not always. In this case, it does. So a process handle will be the same. So you can pass a Win32 process handle and interoperate with an NT level handle for processes. And that all works fine. However, we're again going one level down the stack. If you remember that picture, let's see if I can go backwards. There we go. We started out here with exit and return. We've now going straight to the Win32 API, and now we're going right to here. And so the code here and the code there doesn't know that we're trying to exit. Is that a hand at the back?
It is indeed, Roger.
Yes.
You were saying earlier that it's a 32-bit value. It's actually a long, so it's listening to what you're saying, and because it's a long, it's actually signed. So if it's negative, that means it's an error, and if it's positive, it's exactly matching on to int in positive. That's just something that...
Yes. Yes. We'll come to how you know it went wrong in a bit. Yeah, it may well be signed then, in which case I'm wrong. NT status.
You write the same code basically positive as in the NT kernel layer, and it actually tends to have just right out. Well, I love the NT kernel native API. I think it's beautiful.
So, because we're going below the layer of Win32 and C++ or C runtime, there are certain things that may not happen, and calling NT terminate process may skip stuff. Has anyone heard of this silent process exit monitoring on Windows? Well, you have now. It's a technique where if your process exits with a non-zero return code, you can specify some actions to take, which is quite handy for running stuff on the server. If any process exits with non-zero, I think you can do cleverer things than that, then you can get additional warnings and alerts. But that's implemented in the Win32 layer. So if I call NT terminate process with 42, that bit of code doesn't get called. And you're thinking, that's interesting, I could make use of that. Don't think that. Further down, what happens inside NT terminate process? It looks a bit like this. Your mileage may vary, depends which version of Windows you're running and blah. And of course, it won't be quite the same on 32-bit or 64-bit. We'll come to that later. Basically, we move a register around. We move a magic number, 2C in this case, into EAX. Now, who knows much about assembler? A few brave hands. EAX is a 32-bit register. We're running on 64-bit Windows. But the code that gets passed into the syscall is only a 32-bit value. That's the way it goes. And we issue this magical command, syscall, and then we do ret. So it's not really doing anything. Ah, yes, but the syscall is the magic. That is the instruction, on my machine anyway, that jumps into kernel mode. And it passes the arguments in registers. And in this case, we'll have come in with the calling convention of the outside. We'll have put the 42 in a register and the handle to self in a register. We've moved 2C into a register. We jump into the kernel. And basically, inside the kernel, there's this big fat jump table that says, entry 2C, that's this one. I'll jump to a function that will handle that in the kernel. And the syscall instruction changes to a operating system code page. So you've got privilege levels of ring 0, full privilege. But all the registers just come through unchanged, so you can look at the registers. You also change stack to a ring 0 stack, but again, you've got access to where you were, so you can find more arguments that might be on the stack. And the precise details of how it all works have varied. Depends upon different versions of Windows and different hardware support. Way back, when Windows was new, it used int2e. Who remembers DOS and all the int21? Yeah. int2e just said software interrupt. And again, it would jump into the task handler for interrupt handling, the 2eth entry, and end up in basically the same place. And then people were kind of measuring performance, and it's really quite expensive to do this kind of stuff. And of course, you do tend to call the operating system, occasionally. And it was slowing things down, the transition to kernel mode. So people came up with sysenter, syscall, and I've lost, there's too many varieties. Different versions of people's hardware and different revisions of chips supported sysenter and syscall on different flavors of 32 and 64. But you probably don't care. The important thing is that's how you get into kernel mode. And inside the kernel, there's basically this jump table of typically quite small numbers. However, who's done any programming with Linux and system calls on Linux? And there are numbers defined, nr_open. Anyone know the number for that? I thought somebody might. I've no idea either. You use the symbolic values, and they're included in a header file, and they're stable. That's not the case with Windows. It's 2C on the previous slide on my current version of Windows on my laptop. I have no idea what number the equivalent call would be on any other Windows machine. I don't even know how stable they are. And the people that do a lot of this kind of stuff often issue lists of these are the entry points and their numbers. I'm not interested at that level. I prefer names to numbers, possibly. So NT terminate process. That name is not guaranteed to be stable, actually, by Microsoft. One of the things they say about the native API is we do document bits of it. All the rest, nothing to see here. Move along. There's no guarantee that a given API will remain the same. Some of the older APIs that were there in Windows NT4 have just gone, not there. Others have gained arguments or lost arguments. It sounds a bit confrontational. No, never mind. And you've got to kind of be a bit careful when you start calling the native API. The ones that are documented are the ones that are used by kernel drivers. And the reason being that inside the kernel, you can call a function with exactly the same name. Because the target function in the kernel has got the same name as the original NT, in our case, terminate process that we called. But this time, it's the real implementation. that pokes around with native data structures and process tables and stuff and does things. But the target function in the kernel, it's in trusted mode. You're in the kernel. You can do what you like. So it doesn't need to, the raw lower level implementation in the kernel doesn't need to do any validation because it assumes you got it right. Or else you like blue screens. I mean, it's your call, really. So there's a bit of a layer that does the parameter validation, saying you're coming from user space. They're idiots out there. Or possibly they're malicious out there. So you've got to really check all the arguments and all the permissions. Whereas calling within the kernel, you can bypass a lot of that for speed. Of course, I'm not talking much about the kernel, so who cares? However, it does mean you've got two names to play with. One is exactly the same name function, but you swap NT for ZW. And there's a whole myth about why ZW. And as far as I can tell from poking around the internet, the answer is nobody knows. It was picked to be unlikely to be a prefix for anything else, which kind of makes sense. But it means that in user space, sometimes people call the ZW function, not the NT function, and in user space, it's exactly the same. If you actually dump out the exports from NTDLL, you'll see two names that point to the same function. Because whether it's you call the NT or the ZW function in user space, the kernel is always going to check your workings and make sure you've got the right permissions and you've provided data that you've got access to. So it means that if you're trying to find out something about one of the native calls that you think, A, is either curious, why is that in my call stack when my program crashed, or just, this looks fun, wonder what it does, it's worth searching for both names. And you may find that the ZW one may even be documented on the Microsoft MSDN website. It's possible that they both might be. It's possible, probably more likely, that neither of them will be. But it's a place to try. And as I said, I'm not going to cover much about the Windows kernel because it would take too long and I'm the wrong person to do that talk. And there is quite a lot of information about the Windows kernel available. There's a Windows driver kit. Who's ever played with that? I'm sure some of you have, yeah. There are books such as Windows Internals. Who's ever read one of the Windows Internals books? Yeah, they're great fun. And there's things like NT Insider from OSR Online, although that doesn't seem to be updated as much as it used to be when I was following it more actively. So there are places to go to find more if you're really interested more in what happens inside the kernel. So let's think about argument validation. The API, native API, is the point, apart from the others, which we'll come to, where user space switches to kernel space. Now, when Windows was started, kind of viruses and stuff, they weren't really a big thing. Security was, it was a PC. You know, people didn't care too much about it. The world has changed a little bit since then. So there's a lot of work that goes on in Microsoft to ensure that that API is fairly well hardened. So you can't, in theory, or you shouldn't be able to, do things you're not permitted to by passing in unusual values to the API. What might you do? Well, one possibility would be you could pass in dodgy buffers and crash the operating system. I could pass in file handles I've just got read permission on and ask it to write to it. I could pass in something that requires a higher privilege level than I've actually been granted. I want to open a file in Windows System 32 and write to it. Should I be allowed to do that if I'm a user mode program? And all these kind of checks have to be done by the operating system. And then we finish up, we return, and we put back this NT status value, 30-bit. I've still got unsigned. I must have got a header somewhere with it unsigned. Anyway, and the top 2 bits indicate the sort of status value it is. So 00 means you're good. Normally, all the other bits are 0 as well. Error codes. When I first started looking at the native API, all the functions I came across returned all zeros if it worked. And then it turned out there were one or two function calls that didn't return just 0, but would return a thing like 4, because you were calling get process account. So just naively checking for 0 in my little tool, I had to be cleverer and check the top 2 bits. And if the very top bit is set, it's either an error or a warning. And if the next bit is set, it's definitely an error. So they all start CC. And you've got things like status object not found or status no token. You don't normally see these in Win32 programming. Well, you don't often see these in Win32 programming. How many of people have ever seen an error code displayed, even from a Win32 API, that starts CC? CC00005, access violation, yeah? What happens in the Win32 layer is the error code that you get back from NT is mapped into a Win32 error, except when they forget. Or you jump a layer. And so abstraction, selective forgetting. Occasionally, the forgetting doesn't work, and an error code gets passed straight up from the native layer through to your Win32 call without being translated into something that makes sense in the Win32 layer. So, for example, if you look at the return code from a function that got an access violation, you get some large number displayed in a command prompt. And if you turn that into hex, you get C000005, because the program itself is failing with this NT status value of access violation, and nothing's translating it into a Win32 equivalent error. Some of these errors, but not all, are documented either in winnt.h or in ntstatus.h. Some of them are in both, some seem to be one, some in the other. Others are available by kind of Mr. Google is a wonderful thing. And the great thing about things like that is that there are relatively few hits for that random hex string. Not just one, but you're fairly likely to find a particular error reasonably quickly. And there's a nice function in the RTL support that sits inside the Win32 layer that converts an NT status to DOS error. I mean, just reading out the function tells you what it does. DOS error? Yeah. Win32, really, but an error code. And you can, of course, look that function up and call it yourself. So if you are doing stuff where you need to call an NT API and you want to translate the error code into something that makes sense to the rest of your error handling, you can call that function yourself. For example, if you get back C000034 from a native call, you look it up and you get back 2, which is all everyone knows. Error 2 in Windows is file not found. Whether 2 is any more helpful than C0034, I'll leave to you to worry about. So looking at the sorts of arguments that we can pass into a native API, there's simple values, there's handles. We've seen both of those already. And then there's some more complicated things. More complicated in the sense either they're richer structures or just harder to deal with. So pointers to memory. What sort of memory? How big? What access rights have you got? Is the memory still there because it might have been swapped out? All those sorts of questions. Strings. Strings are fun, aren't they? How long is a string? Where does it stop? And object attributes. We'll come to those. Simple value arguments, they're the simplest. That's partly why I call them simple value arguments. A number like this return code. Many are simply a ulong on the API calls. You pass in various numbers. Quite a lot of calls take an enumeration. So NT query information, and there's a whole set of query information calls for process information, system information, thread information, token information, file information, the whole list. And they all take a different enumeration value. So process information class, for example, contains a list of different values that you can query. And what you pass in is a data structure, void star, something, a length, and the type of information you want. which is a member of that structure. And again, as Windows goes on, they tend to add new ones. Fortunately for our sanity, normally at the bottom. So your old program that called a native API still carries on working because they haven't gone and renumbered all the entries in the enumeration list, but they could, so don't rely on that. There was a talk earlier this week about when you wrap an API that doesn't do quite what you want, do you do it in code or do you write your own wrapper function? And one of the points that was made about writing your own wrapper function is you can use that for regression testing when you get an update to the underlying system and check it still does what you think. So if for some reason you need to use a native call in your own code, I strongly recommend you have a test that validates it still does what you think, and you run it every time Microsoft ship you a new version or minor revision of their operating system, just in case. A few other types. Some of the APIs take a large integer and bool, which as everyone knows has two values, naught and many other values. And then there's a few that have the same type as the corresponding Win32 API, which is nice because it means that's documented, and there's even not just a nice name that you can get out of things like if you run WinDebug with -z to say I'm looking at a file, Ole32 is your friend, because for reasons I do not know why, that DLL and one other contain the PDB information for all these information classes. And you can go DT, process information class, probably with initial underscore for reasons, and you get the list of all the enumeration constants. And you can kind of make a guess from the name of the constant what it might be doing. You may or may not need to know what the data structure looks like. I was having a bit of code. I wanted to spelunk about the system, again, user mode. I wanted to try and find out all the process IDs that were running on the system. As some of you who have also worked in various companies may know, there may be processes running on your system that you don't know about. For security, you know. Some of them don't appear in the official Win32 API, because some of them use these stealth techniques where you remove yourself in the kernel level from the eProcess list, so you're not there. But you are still there as a process. So what you want to do is you want to attempt to open all the valid process IDs and see which ones give you parameter error and which one give you access denied. And there's a subtle difference between those two. And all the ones that say access denied, but you can't find the process ID in the list, are real processes. They're just not ones that you're allowed to see. Can be useful information. However, it's quite a big search space. But there's a system information call that lets you query processes. So you get back a big buffer of formatted data with information about the processes. I don't need to care what the format's like. I treat that as an array of unsigned values. I do a sort unique on it, and that's now a superset of all the possible process IDs. So I use that as my list of things to query. And it saves searching the whole space. It's also stable against changes in the API. You can decide if that's completely crazy or brilliant, I don't know. I wouldn't want to put it in production, but for a little debug tool that you run, to play around, it works pretty well. So, for example, I tried this earlier and then I couldn't get the PDB symbols down, so I'm sticking with what's on the screen. You run up WinDebug. There's also WinTypes.dll, that was the other one. I don't know, that one I kind of guess makes sense. They've put all the type information there, but Ole32 also does it. And you go DT in WinDebug, ALPC message information class, and it gives you all the types. So message SID information, token modified information, direct status information. Yeah. If you're programming in that sort of space, some of these will make complete sense, and you'll think, oh, that's interesting. Wonder how I make use of that. Somebody was telling me earlier today that actually, yesterday, quite a few of the native APIs and the data structures are actually documented in the SMB documentation. because a lot of the wire protocol that's used for file systems is basically sort of just putting on wire protocol what's used in the file system API. So if you're particularly interested in the file system stuff, some of that is covered and publicly documented, but sort of 90 degrees reversed in the SMB documentation. Handle arguments. While in theory, on 64-bit Windows, handles are a 64-bit value, my experience has been they're almost all a 32-bit value that's then sign extended. I haven't tried, but I suspect you could probably mask out the top 32 bits and it would still continue to work, because my suspicion is that on Windows, at least at present, they're going to have to support 32-bit processes, so it makes sense to have an actual 32-bit space for handle values. But that may change as time goes on, particularly if we start getting some machines that are supporting really large amounts of memory. That may just not be enough a space. And again, as I said, they are the same handle values most of the time as the handle values you use on the Win32 API, which is quite handy because it means you can do stuff at the Win32 API, and then there's one extra call you want to make that you can't easily do from Win32, and you can drop down to native API and then carry on. So typically what you do on any of the NT open XXX or NT create XXX is you pass in the address of a handle, and the operating system writes it into that piece of memory, and then you keep passing it in, and then you throw it away. All straightforward, makes sense. When do handle values get reused? Anyone thought about that one? I open a file, I get back a handle value. I close the file. What happens if I try using that file handle? I'll get access denied, some error. If I open another file, what file handle will that have? The same one or a different one? Probably. So there is quite a clever technique that somebody did when we look at security, where you, if you close and reopen file handles a lot, you get back the same handle, but it now refers to a different thing completely. Pointers to memory. You pass in a pair normally. There are a very small number of exceptions, but basically you pass in a length and an address. Of course, it's a C API, so they are two separate arguments. And many, but not all the APIs have a good distinction, which is nice for us, between input arguments and output arguments. So the input arguments don't change, and the output arguments do. They, in general, went for quite a nice model where there aren't that many in-out arguments, but again, it's got a bit messy, and some things do get modified in place. String arguments. Strings are fun. Windows made this decision to go for 16-bit Unicode. That's what they have, and they've got this struct, Unicode _ string. Who's seen that structure before? Jolly good. It's not something you tend to see much in most application programs, because you use your native language way of writing strings, but that's what the native API does for almost all the strings. The exception is the Atom API. Who's used the Atom API? Yeah, where you can register a name with the symbol and get back a number, and then another program can use that number and get back the name. And for reasons I do not understand, that just takes a pointer to a zero-terminated wide string. Everything else, I think without exception, takes this Unicode string. You will notice it was designed back in the days of 32 bits, because it takes two U-shorts, which fit nicely into 32 bits, followed by a pointer, which fits nicely into 32 bits, so the whole thing packs into 64 bits. It's the same structure in 64 bits. But now, of course, you've got two little numbers and a gap, and then a 64-bit number, which is a bit silly, but that's the way it goes. It also means you have a certain obvious restriction on how long a Unicode string can be. U-short. But that's byte length. So there's a 32K really, really hard limit on how big strings can be that get passed in and out of the kernel. And that's not going to change unless they rewrite the whole of their API, because they built that in really in the early days. And I do wonder whether anybody thought about that, or whether it was so long ago that a 32K string just looked like, you know, you could never imagine filling it. UTF-16, and what could possibly go wrong? I have yet to actually come across a real issue in practice with that. I mean, if you've got a file name that's 32K in length, you've probably got bigger problems than worrying about passing it to the Win32 API. Just imagine the error messages. The next thing we're going to talk about is object attributes. Many of the things in the system, you're trying to open a registry key. Well, it's not that simple. I need to pass in a data structure. And unlike the other data structures I've talked about with pointers to memory and a length, this actually contains the length. First thing is an unsigned long, which is the length. And then you've got a handle to the root directory. So you use the Win32 registry. You open a key like HK local machine, /software/Microsoft, and you get back a handle. You then open a subkey and you pass that handle value in to get the subkey. It's the same model here. I pass in a handle that I've already got to something in the same sort of namespace, and that's where the file search or the registry key search or whatever will start. Or I use null handle, which means I've given you the full path. I then give you a pointer to a Unicode string with the name in. And I then give you some attributes and some security description. And the only thing to watch out for is that what they describe as the root directory and the object name may not be completely recognizable to you in your kind of application programmer's hat on. And I'll cover that a little bit as well. And it's a bit of a sad name, I think, calling it root directory, because that kind of makes me think file systems. But it's a root thing, not directory. And unlike Win32, where if I go open Fred, it looks in current directory, there is no idea of current directory. So you always have to provide either a complete full path, or you provide something as the root directory. And there's nothing in between those two. But the full name may be a little bit unfamiliar. For example, backslash, double question mark, backslash. Who's seen that sort of name before? Yeah. You can cause hours of fun for family and friends by creating a file name with 3 dots in it on Windows. Anyone ever done this? You can use this syntax, well, almost this syntax. Create a file name with 3 dots. Now try deleting it. del space ... It says, are you sure? And you go, yes, and all the files in your parent directory get deleted. So what they have here is there's a root bit, and then there's the bit that's known and understood by the file system driver. And thank goodness for this simplicity, at least for our sanity. Once you get past the bit at the beginning for a file name, all the other stuff matches the directory names we know and love on Win32. It's just the bit at the beginning that's different. So another name for this is /device /hard disk 5. I've only got one disk in here. It's only got one volume, but it's number 5. I don't know what the other 4 are. They're partitions of some sort. I've found a couple, but I don't know why it's 5. Anyway, I don't really care, because you very rarely need that. And then it starts with, again, projects ACCU conference 2019. Most of the time, again, abstraction, selective forgetting, most of the time an application programmer never needs to know about or care about or even see those names, but they do occasionally appear, even when you're using the sort of documented APIs. And it is occasionally useful to know about them. So think about security. What can possibly go wrong? I think it was the Windows sysinternals guys who did a bit of a test. They took the native API then, which was I think about 400 API calls, and they just tried all of them with a bit of fuzzy logic. Who's ever done testing with fuzzing? Who's ever found any unexpected, completely unexpected problems? Yeah. They got a lot of blue screens, which they duly reported to Microsoft. They were quite cunning and devious. It wasn't just pure random fuzzing. You do things like you allocate 2 pages in memory with entirely different memory characteristics, and you give a buffer that starts here and goes into the next page. And of course, if you're a little bit careless in your checking in the OS, you check the first byte, and yeah, it's writable. Right. And suddenly you're now writing into read-only memory, which maybe you've mapped one of the OS, bits of system into your program at that address. They have improved things a lot since then, partly because of people like them, and partly just because of the increasing incidence of security outbreaks. So I think it's quite unlikely now that you'll find a vulnerability, but it's just interesting to think about the things that people have had to come up with. And this is leaving aside completely any attempt to cover the hardware level vulnerabilities that I'm sure there are people in this room who could probably talk about far more than me at great length. Just looking at the software side. So simple value arguments. It's much the same as any program. If I've got a function that takes an argument, I probably want to do some sort of range checking on it to avoid things like multiplying and falling off the top of the 32-bit value, or looking it as an index into something and going off the end. And it's much the same here. So ZW or NT create event, this is one of the ones that is documented somewhere in Windows land. I've got an event type and a Boolean initial, Boolean, great. Let's see where I pass 42 in as the value of that thing. What will happen then? Don't know. Might be exciting. How about event type? I think it's an enumeration with about 3 values. What happens if I pass in 17? Don't know. Let's find out. So there's quite a lot of possibilities that if the implementers hadn't been very kind of clever or checked it, you might be able to do bad things with Windows. So again, they had to be a little bit kind of restrictive in checking the valid ranges of all these things. Handles. They're a bit more complicated because they are my opaque value that refers to something that the OS has opened for me, like a file handle or a device. And earlier checks, what happened was you arrive in the API, you look at the handle, you look up the handle, so yeah, it's a file, you're doing a read call, you've got read permission, job done, tick, move on. And then some clever people said, we've got multi-threaded programs now and we've got multi-threaded hardware. In my other thread, I will close and reopen in a really tight loop. And I'll hope to get a new entity owned by that handle, but that I'm not allowed to do that operation on. So I will pass a file handle to c/temp/whatever into a write API, and in another thread, I will close that file handle, I will open c/windows/system32/ntdll.dll, and I'll keep repeating the open close until I get back the same file handle. And if I'm lucky, in the kernel, it will at that point be attempting to write to the file handle it validated earlier. Clever, isn't it? So now they don't do it that way. I believe they now duplicate the handle value to an internal value, which they then use from then on. So it's just a kind of example of some of the things that you probably, unless you work in security, don't even think about as an attack vector. Pointed to memory, as I said, there's a few more issues there. Have you got access to it? Has it got the right permissions? Can you write to all of it? And you've got to make sure again, in the kernel, they've got to worry about this. You don't. Your application program assumes all the memory's there. It might get swapped in and out. But if you're in the kernel and you've got a pointer to some user data, and by now you've swapped context a few times, and you're in a different process context, and you've got this address to memory somewhere over there, and I write to it, it might not be swapped in, etc. So there's got to be quite a lot of work going on under the covers to handle that. Fortunately, we don't need to really worry about it. The other thing is about the full range of addresses, which is, again, part of the reason why the API tends to take a buffer and a length, because you're being explicit upfront about the length, so it can check you really have got the right access to the whole of that buffer. It knows what the page size is, and granularity is the page size, so it hasn't got to check every byte. Checking each page is enough. And that probably do. String arguments. Strings can contain funny characters. What happens if I put a null character in the middle of my UTF string? Is it still a UTF string? Yes. Will it work? Maybe. There was an early bit of code, some sort of malware or virus. It wrote entries into the registry that ended with a null character using the native API. You could view them, because the query API would give you back a string with an extra null on the end. But of course, as soon as you went back into Win32 land, you end up with a null terminated string that's just 1 byte shorter than the real string that's in the registry. So you could view them, but you couldn't change them. Unless, of course, you used the same native API and built up a Unicode string with an extra null character on the end. And you can do sort of weird, horrible things. Some of the APIs are more restrictive than others about which characters. So if you try with the file system, for example, there's quite a lot of characters that they actually explicitly check. You can't create a file name with, colon and slash in, because it just wouldn't make sense. And object attributes, a bit more about the object namespace. There's a whole set of different namespaces in the kernel. Things like device, event, key, mutant. I love mutant. This is a mutex, which you've probably heard of, and it's called a mutant for historical reasons, because the person that was writing the code didn't like the way that mutexes had to behave in order to support, I think it was the OS2 subsystem. So he described it pejoratively as a mutant, and that went into the kernel namespace, even though in our user space it's mutex. Section, semaphore, symbolic link. Most of the time, most application programmers will not care about these. There's a nice tool from sysinternals. Who's used sysinternals tools? Yeah, they're great, aren't they? How do you do Windows development without them? I've no idea. WinObj. Who's used WinObj? Okay. For the rest of you, here's an example. I just ran up WinObj, and you get a slash at the very top, the root of the object namespace, various names down here, and then there's one global question mark, which you might think is this global? No, it's the double question mark. And that's the one that appeared in that earlier file system name, backslash, question mark, backslash. It was actually a subnamespace in the system namespace. And inside global, you've got, for example, our friend C:, and it's actually just a symbolic link to, you guessed it, /device, hard disk, volume 5. And in fact, a significant proportion of the things you see with WinObj are merely symbolic links. Symbolic links to symbolic links to symbolic links, and eventually somewhere you hope to find an actual device driver. And the way it works is that a number of the Win32 APIs will pass stuff that's got the question mark down to the native API, more or less unchanged, which can be quite useful. So we saw earlier, backslash, question mark. And the top level one is this global namespace. What happens is it finds the entry in the WinObj namespace that matches as far as it needs to go. And then the rest of the path is passed off to, in that case, a file system driver. And so the file system driver you get then understands the project's ACCU conference 2019 bit. Or if it's a file system driver for the network, the redirector understands the rest of it. In the registry, you've got one entry in WinObj, as far as I'm aware, for the registry, and it's just the registry. And there aren't any subkeys. The subkeys are all provided by the driver for the registry. Or am I wrong?
Do you know Kernel server? I seem to recall they do some quite clever stuff with showing you different namespaces. Do you know that?
Yes. If I go back one, global. There's also local. And there's some virtualization that happens, particularly with terminal server. And if I were to expand sessions, you'd probably find that there might be one or two different sessions. So some of this stuff is system-wide, and some of it is a bit more local. We'd run out of time if we went much further into that. So here are a few other aliases for the same actual disk. I just looked around. It's also my boot device. It's also the boot partition. It's also volume GUID. You can use any of those names in the NT API to name the root of C. This may be useful. If I take a disk out and put it back in, is it the same disk? If I remap my drive letters, is it the same drive letter? You know, the GUID might be a bit better to use for certain purposes than the name. Typically, all these names are set up when the system is started and initialized, and you don't get much chance as an application program to do much more than maybe just kind of query them. And as I said, most of the Win32 API doesn't use them. Just for fun, to keep you on your toes, they decided, I don't know why, to change it when it hits Win32. So it's double backslash question mark rather than backslash question mark question mark. I mean, you know, otherwise it'd be too straightforward, right? So if you go to your favorite Windows command shell and do dir backslash backslash question mark backslash C colon, you will probably find that you get the root of C. But you can also try some of the other names that are in the WinObj viewer for the global namespace. And if you actually ask what's being opened at the native level, you'll get a different name. So what's happening is the Win32 API has got enough smarts to recognize this syntax, and it just changes that for that. I personally suspect an accident with backslash somewhere in the C code, but it might be deliberate. And it's not just the file system. Most of the things, anything in the Win32 API that takes a name is keyed somewhere off the system namespace. So if you create a semaphore, then it adds it to the namespace. So I have a call create semaphore 001 example.semaphore, and then look for it in WinObj. I find that under sessions, session 1, I've got base named objects, and it's example.semaphore, and it's a semaphore. Okay. Which is how you can find named objects, because if I run another process in the same session and it asks the operating system for example.semaphore, it will be looking in the same key in the namespace. Right, well, categorizing the native API. It is, of course, a very small API because you're just accessing the operating system and it's nicely, you know, encapsulated, and there are only about 500 functions or so. There isn't really a clear categorization. I've got a little tool I wrote that I trace some of the calls to it, and I've loosely categorized them. So you've got things like atom for the named atom services, maybe memory. There's quite a few calls to handle memory. Allocate memory, shared memory, deallocate memory. Security, quite a few. Process, you would be hardly surprised to know. Quite a lot of calls about processes, duplicate processes, create process, open process handles. synchronization, the registry. You get the picture. And WOW64, I'll talk about that a bit more in a minute. But wait, there's more. That's just the bit of access to the native API that is provided by NTDLL, or what you might call operating system-y sort of things. We've also got several other ways of getting into the kernel. One way is, Windows is, after all, called Windows for a reason. It's got this kind of GUI thing, and originally that was a completely separate and kind of user mode thing, but very rapidly, for performance reasons, a lot of it got implemented in the kernel, and they wanted a quick way of getting from user space to kernel space. So they took exactly the same model, and there's a whole another set of functions, NT-user and NT-GDI, that have another range of numbers. They start at 0x100 something. So they just partitioned up the space. On older versions of Windows, there were two separate DLLs that provide this, GDI and user. On newer versions of Windows, they've got one DLL that provides it, and the old entry points just forward to it. You've also got the Windows subsystem for Linux. Who's used that? Who knows much about how it works? It's magic, right? Yeah, and that's all you need to know, really. The thing is, in Linux, you move a value into the AX register, and you invoke a syscall, and you get into the operating system. That's great. Problem is, on Windows, you move a value into the AX register and call syscall, and you get into the kernel. And the numbers, of course, overlap like mad. And the ones in Linux are published. What are we going to do? So the approach was, well, let's just keep them apart. Inside the syscall handler, it can tell very quickly whether the calling process was one of these WSL processes or not. And if it is, it jumps off to these two device drivers that implement the low-level Linux stuff, and it has a big lookup table in there. And if it's not one of those processes, it goes off to the normal handling and looks through the jump table for the NT XXX functions, which means suddenly the attack surface for Windows has roughly doubled, because you've now got all the native API calls plus all these Linux emulated calls in LXsys and LX Core. So unsurprisingly, a number of companies are being a little bit reluctant to fully adopt deployment of WSL in their production environment until they're confident that they've managed to capture all the issues, potential issues with security on the WSL subsystem. Who's used Cygwin? That does it completely differently. Cygwin uses a lot of the native API. So it is actually not exactly Win32, but it's just an application mode processes that calls the NT calls. So it doesn't really break anything odd about the Windows security model. You can do more or less the same things with a normal Win32 program by calling into the NT API as you could do with Cygwin. Of course, that's partly why WSL is better, because you might have to make several calls from Cygwin in through the NTDLL layer to get one thing done. And on WSL, it's one call into the kernel, and now you're in the kernel. You can do the whole thing in there. But I'm not going to cover those in much more detail. So, as I said, there's this Windows user and Windows GDI. I'm not sure the distinction really makes that much sense now, which is probably partly why they've merged together. Again, I think it's quite common in that space to find a much closer name correlation between the user mode function and the underlying user or GDI NT function. And they have quite a wide range of data types, but again, they're typically the same data type that you would use in the Win32 world. But I'm not that interested in that side of things. It doesn't help me very much. I think I'll move on from that, and I've covered most of that. WOW64. I'll spend the next few minutes talking about WOW64. Who thinks it's amazing that we can run 32-bit programs on 64-bit Windows? Who thinks, why are we doing this still? Yeah. I still can't decide whether it was a stroke of genius or insanity or both. Who remembers back to when OS2 went to 16 to 32 bits? Yeah. What they did then was very clever. They did this thing called tiling, where they mapped the 32-bit address space into 16-bit segments. So there was an exact mapping between addresses, 32 to 1616. And apart from a bit of work in the thunking, where you had to make sure that your data structure didn't cross a segment boundary, it was a conceptually quite simple way of mapping your 32-bit and 16-bit process together. And I think I'm right, you could actually, if you were careful, load old-style DLLs into a 32-bit process, and things just kind of worked. WoW64, I don't know whether they just couldn't find a way of doing it or they just decided to do it differently. What they do is they load a 32-bit process that you wrote back in the day when you had a 32-bit version of Windows, and that was all you had. And it loads it into the low 4 gig of linear address space. But it can't load it anywhere else because you've only got a 32-bit address to refer to anything. So it would be pretty pointless to load it in high memory. So you load it in a low linear address. And you set up the code segment on the kind of AMD style 64-bit to interpret the instructions in the old 32-bit world. So as far as you're concerned, you are still in 32-bit land. So you go on, you run your program, you make exactly the same calls as usual to functions in a 32-bit address space. At some point, it is likely you will want to call the operating system. Who'd have thought? I mean, hello world. I'm going to, at some point, issue some I/O. So I make a call to the 32-bit operating system. There is no 32-bit operating system. But it seems to work. And that's because it hooks the call. It doesn't go anywhere. Well, it does. It jumps off and ends up in 64-bit part of your program. What? I've got a 64-bit part? Yeah, but you can't see it because, of course, it's outside your 32-bit address space. It's very clever. Sometimes possibly too clever. But basically it works. So I tried drawing it. I don't know whether I succeeded or not. Here is my 32-bit bubble. I am writing my program.exe, and I call into Kernel 32, which is where a lot of the Win32 API is done, and that calls into NTDLL, the 32-bit NTDLL. And that does the normal jump to the operating system, which, as we saw earlier on, would be like a syscall or a sysenter or an int2e. It just does a far jump to Magic Land. And Magic Land is implemented in WoW64 CPU.dll, at least on the machine I'm using. There are a couple of other ways of doing it, I believe. And that is the only bit of the WoW64 system that lives below the 4 gig limit, because it's the only bit that has to. Somehow, I've got to get from 32-bit land to 64. Well, that bit has to be in 32-bit land. So magic happens here. I'll talk a little bit more about that in just a moment. And we end up calling WoW64 Win, which calls WoW64 DLL, which calls NTDLL, the 64-bit NTDLL that actually gets into the operating system. So what can possibly go wrong? So in my NT terminate process, if I compile my program with a 32-bit compiler and follow it down the debugger, I move another value. Remember, if you've got a good memory for numbers, what was 2C? It was NT terminate process in 64-bit land. And what they've done on WoW is they've put some extra bits in the high. I have no idea what they mean. Presumably something about how to interpret this, but they seem to be using the same number here. And then they move the address of WoW64 system service call. And then they call that function. And what it does is it contains a jump into 64-bit land. So it does a far jump to a 48-bit address, which is a selector and an offset. And it's set up so the selector is a code segment that says, treat this as 64-bit. So the chip flips into 64-bit mode. It's now got 64-bit addresses. It can now jump into the high memory where WOW64 CPU and NTDLL and all the other stuff lives. It's also got to load a different data segment because, of course, the one you're running in your 32-bit LAN knows about 32-bit values. So you have to swap that, but the key part is done by the swap to CS. And then when it's finished poking around and called NTDLL and got the return back, it needs to unwind everything and give you back your value. So NT status, that's easy. I can just pass that back through registers. But if I've passed in a data structure that's got populated, how wide are the elements of that data structure? Well, they're probably 64-bit wide, and my program is expecting 32-bit wide. So I've got to do quite a lot of manipulation of the data structures to pack them down, change lengths, etc. Sometimes this jump to 64-bit land is referred to as Heaven's Gate. Sometimes people restrict that strictly to the cases where malware writers are doing the same thing. Your mileage may vary. So, sort of things you need to do is zero extend or sign extend 32-bit values. Convert data structures from the 32-bit to the 64-bit. Think about that Unicode string, U short pointer. Well, it's U short gap, and a pointer is not just a pointer, it's now a 64-bit pointer. So you've got to do a bit of translation work, mechanical translation work. Someone's got to write that. Microsoft have done it for all the native API calls. Looking at object attribute, its size, it's 8-byte string for Unicode, 24 for object attributes, and it's now become 16 and 48. So there's quite a lot of work. So it will be slower, a bit. And of course, it's making two levels of call. But the fact it works at all, I think, is pretty good. And then on reverse, you do the whole thing back again. And usually, it's transparent. There are one or two cases where you get one of these kind of warning modes. So you get an error back saying not enough memory available. And there are at least one or two cases I know of where it doesn't completely do the translation back, or didn't, maybe by now. But just to make it more fun, the layer also does some other mappings. So there's this virtual 32-bit file system structure. Who's come across this? syswow64. I don't know who thought it'd be good to put all the 64-bit binaries in system32 and all the 32-bit binaries in syswow64. But if I ever meet them, I'll have a word. So what happens is if you've passed system32 in any of your file system APIs, it gets changed to syswow64. If you've used things underscore in software in the registry key, it gets mapped to software WOW6432 node. So you get this fun where you use a registry viewer and you put something into the registry and then you run your 32-bit program to read it out and it's not there because it's in the other bit. The reason for it is so that things like existing installation scripts would just work. The full list of rules as to what gets mapped and what doesn't get mapped is long and complicated and not stable. So I refer you to the Windows documentation, which does document it quite well if you need to know.
Just use the parameter to get to the same thing.
Yes. There is also something you can do in the WOW64 native API. So there's some extra functions that the 32-bit Windows API provides, designed deliberately just for 32-bit programs that know they're running on 64-bit Windows and want to make use of that. So, for example, WOW64 disable WOW64 FS redirection. I mean, you can guess from the name what it does. If you call that, then the calling thread now uses the real name that you gave, not the modified name, until you turn it off again. And similarly, there's a reg disable reflection thing that lets you turn off the reflection on the registry. And there's a couple of other APIs that are occasionally useful. you can, for example, query the native system information. Because I'm running in 32-bit land, when I call the NT get system information call, it gives me information about my kind of virtual 32-bit land, like what's the highest virtual address I can have. I might want to know what's going on under the covers in the real 64-bit OS. And so that API can get me that. I mean, hand waving, loosely what happens is when you call the NT query system information in 32-bit land, it calls the underlying 64-bit one and then munges the parameters and the values. And when I call this thing, it calls the underlying query system information and gives me back the raw values, more or less. You can also call ntwow64 read or write virtual memory, which means a 32-bit program can attach to a 64-bit process and fiddle with read or write memory in that process address space above the 4 gig address boundary, which if you're doing kind of debugging and monitoring tools can be very useful. Talking of debugging, you can debug a 32-bit program with a 32-bit debugger. You can debug a 32-bit program with a 64-bit debugger. You can get confused because, for example, there are 2 copies of NTDLL in your target process in the 64-bit land. One's the 32-bit one and one's the 64-bit one. You can't debug a 64-bit process with a 32-bit debugger. It's just, you can't do it. Not without writing a whole slew of native stuff. Unfortunately, the error codes you get back when you try it are unhelpful. Okay, quick bit of documentation. It's just coming up to 1. I'm going on a little bit because we started a little late because of tech. I hope that's okay with people. If you need to go, then feel free to rush out. There's only a couple to go now. Documentation. The Windows driver kit does now document a proportion of the native API. Basically, the calls that they think device driver writers will need are documented, and some of the other ones are documented. Many of the functions have been re-engineered by Reactos. Who's come across Reactos? Yeah, written by Russians. What more do you need to say? It's great. And I've used quite a lot of the stuff from the Reactos project to get some idea of what the native API actually does. Undocumented.ntinternals.net. You can guess what that does, can't you? And there's quite a few other websites, particularly ones on software security, because for fairly obvious reasons, while it's fascinating and I love knowing what's going on under the covers, some of the people that want to know what's going on under the covers and wanting to know so they can subvert all sorts of other security things. So be careful poking around about the native API. Tooling. I remain surprised at how little tooling there is at this level because on Linux, I use strace quite a lot. Who uses strace on Linux? Yeah. Or similar tools that use that level of API. The really important thing as far as I'm concerned with application program is what interaction is it making with the rest of the world through the operating system. I'm not really fussed about the Win32 layer if I'm debugging interactions between my program and the rest of the programs. There are a few tools. There was one called strace for NT from BindView, but that doesn't seem to be under active development. There is a DR strace from Dr. Memory that I failed to get working on either of my machines, but I believe it should work. There's strace NT from intellectualheaven.com. And I've got one called NTtrace that just uses the Windows debug API to patch all the codes for the entry and exit of the native calls and dump out the arguments, a bit like strace. And there are some commercial tools. So if you're interested in that, there are places you can go to get some information. And there may be a new one I've failed to find because it does change a little bit. And I should conclude because I'm sure you want lunch. So thank you all for your attention.